So, last class we looked at essentially balancing the effect of gravity on the mechanism using counterweights, right. So, that because the system will tend to go to its position of minimum potential energy. Okay. So, by making the Cg of the system constant, you know that then there is, it will stay at whatever position it is put in. So, that was the principle behind doing the balancing. That was how we achieved the balancing, by keeping the Cg up. So, we did that for a single link, and then we looked at doing it for the 4 bar linkage. Now, using counterweights is one option, but it also adds mass to the system, adds, increases the size. It also so it is not as desirable always to do it using counterweights. And today we will look at doing similar kind of balancing, but using springs, because springs give you some more flexibility. They do not add as much mass to the overall system. So, they have certain advantages. They also have certain disadvantages, which we will look at. So, suppose we have a link, so a rotor, like we so we have a link or a rotor, say with the, this is the mass center. Okay. Now, and it is making a certain angle theta with the vertical. Okay. Now, I want to balance this link, okay, using a spring. Okay. So, essentially what I need to do is, this weight exerts a moment about A. I am trying to balance that moment using a spring, using the spring force, but I want to be able to do it for all theta. So, the idea is, if it is balanced, then no matter what the theta is, if it is perfectly balanced, it will stay at that position. That is what we did. So, when we did it last time with the counterweight, we essentially did that. So, if I had a link like this pivoted about A, I would just attach a counterweight to it like this, right, such that the moment due to this would be balanced by the moment, the clockwise moment would be balanced by the counterclockwise moment of the counterweight. So, same thing we are now trying to do with the spring. Okay. So, if I see here, so let me call this distance B, this distance A, like we do in triangles, right, AB equal to, yeah. So, and so if I look at the moment, I want to balance the moment about point A should be 0. Okay. So, and let me call this distance AZ as R, that distance is R. Okay. So, I have this is the so I had the force to wait. C, and I have the moment arm of this force, the spring force, let us call that D. So, D is the moment arm of the spring force. So, I have the moment to be balanced is mg r sin theta, okay, due to the weight, and that has to be balanced by the spring force times D. Okay, the spring force would act along BC. And let me call this angle phi. Now D, okay, so D equal to C sin phi. C is this length AB to AB, B equal to AC, and let me call this A equal to BC, and R is A to C. Okay. Now, if I look at this triangle, I have B by sin phi equal to triangle ABC is equal to A by sin theta, okay, by the sine rule. Therefore, sin phi is B by A sin theta, and therefore, in terms of theta, this equation now becomes everything in terms of theta. I get mgr sin theta is equal to Fs and D is BC by A sin theta. Okay. So, for theta not equal to 0, because then I can't cancel sin theta, I get mgr equals Fs BC by A. Okay. Now, the force in the spring will be, the spring will have some, regular springs will have some spring constant, and it will be proportional to the, so A naught is say the free length of the spring. Right. So, I can write this as this is equal to K into A minus A naught by A BC. Okay. Now, if I look at the expression for K, okay. So, I want to find what would be the spring I need to use in order to be able to perform this balancing. If I can make the spring proportional to the length, basically if the spring is linear such that F equal to K A, that is if A naught equal to 0. Okay. So, the spring force is proportional to its length. not to its displacement from its free length. So, the free length is 0 basically. If A naught equal to 0, then I get k equals mg, what do I get for k? So, k, A and A will go, right. So, I will get mg r by bc. Right. Now, if you look at all this, this is all constants, right. So, I could use a spring of constant stiffness equal to this, provided its free length is 0. So, there are some, the springs can be wound in such a way that the initial tension is proportional to its free length. That is essentially what we are looking at, right. So, if when the spring is at its free length, if it applies a force which is proportional to its free length. So, if F equal to k s naught, F naught equal to k s naught, that is the force it applies when it is, then you have this condition, or in other words you can such a spring where A naught equal to 0 is called a 0 free length spring. So, that is the challenge when it comes to using springs for balancing. You can only use these special springs. So, there are ways to achieve the 0 free length. I will just show you now how you can use a regular spring and make it 0 free length. But it is that's what adds complexity to balancing using springs. You can perform approximate balancing with regular springs by using optimization and trying to find where to attach it, so that over the range that you are looking at, your potential energy is fairly constant. Potential energy fairly constant implying that it will not move from that position, because otherwise the system will seek, if it is only under the action of gravity, it will seek the point of lowest potential energy. That is what you are. So, when you say you are making the Cg constant, all these mean the same thing. Essentially the Cg remains constant, the potential energy remains constant. Okay. We are only talking about balancing the effects of gravity. Beyond these external forces that you have, those you do not have control over. You are talking about the system masses, and so that any, you are trying to basically balance out the effects of gravity on the system. Okay. So, this is, so such springs are called 0 free length springs, and so you can use a 0 free length spring which has this spring constant to balance a mass m that is located at a distance r. So, for a single link you can perform the balancing in this manner. So, now how do we achieve this 0 free? So, either like I said, you could have special springs made, but that is not always an option. So, another way to achieve this is to construct the spring like this. So, if I have the link like this, and through a pulley okay. So, now when it is folded, so when theta is close to 0. The string, it is an inextensible string attached to the spring. Okay, it is an inextensible string attached to the spring. So, what this sees is only the extension S minus S naught will be this distance. The A that we are talking about between those 2 points will be A minus A naught of the spring that you are using. It is only the extended part of the spring that comes into play in this region. Okay. But obviously, it requires more effort to locate to attach a spring in this fashion. So, that this is the mass. Okay. So, this is one way of achieving this 0 free length condition using a regular spring. So, this is an inextensible string attached to the spring. Okay, so, this distance is the extension of the spring and the force will be proportional to that extension. Okay. So, this is one way of, so you choose a spring of stiffness K equal to mgr by bc, that is constant, and place it outside the line, let us call this WV connecting the link and the fixed reference. So, this is one way of realizing a 0 free length spring. Okay. So, if you look at the literature, there is a lot of literature on balancing using springs and all that. Exact balancing is only possible using 0 free length spring. So, in the literature on balancing, you will come across this all the time. So, in many cases they will just assume that 0 free length springs are available or that you can create it using some way of doing it. Okay. There are ones with you will actually, for more exact balancing, you have to have like 3 pulleys to get it because of this angle, that the wrap angle. So, they will take that into account and all that. So, you can go, if you are interested, you can go look at how to achieve exact balancing using but 0 free length spring. So, in most literature on balancing, they will only say this applies with 0 free length springs and assume that all the springs that are being used are 0 free length springs. Okay. So, you will come across this in the this is what 0 free length springs mean. So, it is a spring that is linear. So, it is proportional to its length. The force that it produces is proportional to its length, not just its extension, right. Okay. So, you could achieve the same in by other means as well, in the sense locating single link. A, B, sorry, this is A, B, C. So, this is R, this is B, this distance is C, and this is A. Okay, and theta is the angle with the vertical. Of this same thing, you will get the same result if you do this. The reason we will see how to extend it to more than one link with this. So, some of the applications of this kind of balancing you will see, any of you have those desk lamps which have the springs on them. So, you set it at any position, it will stay there. It will have, you know, it will have 2 degrees of freedom generally. You can fold it, you can and you can set it at any, you know, there will be 2 degrees of freedom for that, and you can set it at an angle and it will stay there. It is quite easy to move also. That is an example of a balanced 2-link system. Similarly, you know, this could be the case for say a microphone, where you are adjusting the position of that, right, and it stays there. So, those are all examples of where spring balancing is used, okay, this kind of gravity balancing. So, you change the position and it stays there, it does not just fall over. Okay. So, again in this case you can very easily see, you do the same moment balance, you will find that the force in the spring should be mgr by bc into A, which means it should be proportional to the length A, which means this should be the stiffness, it should be a 0 free length spring of this with K equal to mgr by bc. Okay. So, you can extend this, So, one way is, you know, you suppose you have 2 links. So, you have 2 degrees of freedom, you have a theta 1 and you have another link. So, in many cases in robotic arms and all that, right, you do not want the actuators to have to move the weight of the arms as well. They have to move, there will be some external load, but you want the actuators to not have to do extra work to actually deal with the weights of the arms. So, that is why you do the balancing for the basic weights of the links in the robot, and then on top of that you have actuators to move them beyond that. You know, you may have external loads that you are trying to. So, if we look at this, can be extended. So, essentially here you have a vertical fixed link, okay, or a link that stays vertical, okay. Here you have this fixed link, and then you have a spring that comes from there to balance this link. So, now if you want to balance more than one link like this, okay. So, I may have a link here and then another link. So, a 2 degree of freedom system. So, should I do this? Okay. So, I have here, so say this is my fixed, okay. I have a link like this, and then I have something like that, okay. And then I have. So, what I could do is I balance this link. Okay. Now, I need another vertical link here. Okay. So, one way to achieve that is to create a parallelogram. So, I would do that, okay, and then use another spring here to balance this. So, I have a degree of freedom here, right. So, this may be theta 1, this may be theta 2, okay. And so, I can, so these are called auxiliary links. So, I attach these other links to create this kind of a parallelogram arrangement. So, that because this will always remain vertical, this link, right, because it is parallel to this fixed link. So, I can have, and I can also have a degree of freedom. So, I could do this, I can and in each case start from the end and start sort of find the k for each of the springs depending on what is beyond that. But I could also do, I could add a degree of freedom in that direction. I can have rotation and it will still not change the balancing. So, I have, say I have this stand with these two links. The additional degree of freedom that I have about this longitudinal axis will not affect the balancing. Okay. So, I can have additional degrees of freedom in that direction without affecting. So, I can move this entire, so this is where robots etc. use it, because they will have a degree of freedom about this axis and then they will have manipulator arms with the rotations about these axes. So, this is in the plane and then I could rotate that as well perpendicular to this about this axis and still maintain the balancing. Okay. So, that is so it, like I said, there is a lot of literature on balancing, especially with the springs. So, those who are interested can look that up. Okay. So, that is essentially what you would do. So, if I have mg here, so this would be my, let us just call this B2, C2, A2, this is my original A1, this is my B1 and this is my C1. Okay. So, say that, so this is theta 1, this is theta 2. Okay. What is the moment I am trying to balance here? The same thing. So, I would use, take this, find this spring, okay, that would balance the moment of this about A2, okay, and then I balance the moments about A1. So, if I look at the what is my moment arm of spring about, find the moments about mg. So, the moment to be balanced is what is that equal to? Mg r2 sin theta 2 plus r1 sin theta 1, right. If I take where else have you seen practical applications of using springs for balancing? Have you seen a car hatchback? Why is it so easy to lift? You will see a gas spring there. Okay, otherwise it's a lot of metal for you to lift, right? The reason it's easy to lift is because of, so you will see lots of applications of balancing. What would be K1 and K2? F1 B1 sin theta 1 by A1 plus F2 using the same notation. Mg R1 sin theta 1 plus R2 sin theta 2. So, if this has to hold for all theta 1 and theta 2, okay, if you want balancing, you want this relationship should hold for all theta 1 and theta 2. Therefore, I can just say that the sin theta 1 terms should be equal and the sin theta 2 terms should be equal. So, if I equate those, then it will hold for all. F1 should be equal to mg R1 by B1 C1 A1 and A2. Again 0 free length springs, directly proportional to A1, directly proportional to the total length A2 in each case. Okay. So, you would use 0 free length springs. Instead of doing this, you could also, if you have seen the lamp, you will see that both the springs are actually attached to the base. So, this is a bit cumbersome because you are attaching the spring to moving links. Ideally, if you can attach everything to the base, okay, that is better. So, you will have configurations like, so there now you would draw the, so I have my A, so I have these two links. And this is B, okay, let us call this B1 and B2, okay. And here okay, such that this would be parallel to that. So, again spring 1 equals V1 C1 by A1 . Mark it here. Sin theta 1 plus R1 sin theta 1 and to hold for all values of theta 1 and theta 2 . C2 A2. So, this will be K1, this will be K2 of the spring. Okay. Having to use 0 free length springs can make a design quite complex, because if each of these you imagine you have pulleys and strings, it can make the design quite complicated. So, the usual way to deal with it is to use regular springs, and then you get approximate balancing. So, not perfect balancing, you cannot get perfect balancing with regular springs. Okay. So, you may not have perfect balancing, but you can get pretty good approximate balancing with regular springs. Gas springs also have certain advantages over extension springs, and mostly what we have used here are all extension springs in this particular example. So, gas springs have certain advantages because they are very compact, they are but you will not get perfect balancing with them either. So, it's you can get a pretty good approximation. Okay. So, now you know how to balance a single link, right. yesterday what did we do with the 4 bar? We showed that the unbalance in the 4 bar, due to the coupler which is the floating link, its effect can be captured in terms of masses that are attached to link 2 and link 4, right. So, I can attach a mass mass M3 at a specific location to link 2. Similarly, so I can capture the effect of the coupler. The effect of the coupler is equivalent to balancing a mass M3 that is located and moving with link 2 and another mass moving with link 4. Now, again link 2 and link 4 are rotors moving about fixed pivots. So, I can do the same thing. I can now, instead of for this mass, so now I would have to take into account the mass M2 of link 2 in addition to the contribution from link 3, the M3 located, find the combined CG of those two on link 2, and now that is just a single link with a mass. So, I can use a spring to balance that. So, to balance this 4 bar, I would attach a spring to link 2 and a spring to link 4. 0 free length springs I can attach to link 2 and link 4 to balance the effects of the motion and still get the same constant CG. So, instead of using counterweight. So, you can, what we have essentially done is shown that okay, if I can balance a rotor using counterweights, I can do that using springs too. And for the 4 bar, essentially we have reduced the balancing. The unbalance is due to some equivalent masses on link 2 and link 4. Okay. The rest of it is of course constant. I am looking at balancing the moving masses. So, if I do that, then I can do the same thing. So, I can attach a spring to link 2, I can attach a spring to link 4 such that it will balance this combined mass. So, for link 2 it will be M2 plus M2 located at whatever its CG is just of link 2 plus this additional mass M3 located at this R2 dash at Z2 plus R2 dash, right. And for link 4 again I will take into account its mass M4 plus this M3 located at Z1 plus R1 dash, R4 dash that I had here. So, for each of those links I would take those combined masses and then balance them using a spring like we did today, using a 0 free length spring. In that case, then for the motion, of course practical considerations, if this thing is moving 360 degrees, how do you, all those are there. So, it is in the range that you are interested in. Okay. So, today when we looked at the single link, we were looking at theta from 0 to 180 essentially. So, there will be practical considerations in every problem which will which is why optimization is probably the reasonable approach to take, the better approach to take, because then you can put in all your constraints with regard to, you may not always, the spring that you find out that you determine is necessary for exact balancing may not always be practical, okay, in which case you have to look at other solutions. Okay. So, that is what I wanted to cover with respect to gravity balancing of mechanisms.